Okay, so in this lecture I am going to be going over battery energy and power. So, battery ratings. Sometimes you'll see battery ratings in amp hours and very much more commonly milliamp hours rechargeable small batteries like AA batteries and AAA batteries in milliamp hours. And the question is, what does this mean in terms of energy or power? So, charge equations. I'm just going to go over some charge equations briefly just to get some concepts in place. Okay, so the SI unit of charge is in units of coulombs. I abbreviate that as CO. 1 coulomb equals 6.24 times 10 to the 18 electrons, which of course, yes, is a very large number. The electron charge is going to be equal to 1 coulomb per 6.24 times 10 to the 18 electrons, which equals 1.602 times 10 to the negative 19 coulombs per electron. The charge of an electron is negative, so one electron has a charge of negative 1.602 times 10 to the negative 19 coulombs. And so one last thing here is that 1 amp equals 1 coulomb per second. That's a flow rate. Okay, so now I'm going to do a charge calculation. If a 1.2 volt rechargeable AA battery can deliver 1700 milliamp hours for an hour into a load, how many coulombs of charge would it transfer? So the amount of coulombs that it would transfer is going to be the integration of current from time 0 all the way up to some other arbitrary time 1. And so when we do that, we get 1700 times 10 to the negative 3 coulombs per second times 3600 seconds minus 0 seconds. And so that's just simply 1700 times 10 to the negative 3 coulombs per second times 3600 seconds, which equals 6120 coulombs. Next, the energy calculation. So how much total potential energy does the same battery contain if it is rated at a consistent 1.2 volts over this time range? So I'm going to take voltage, multiply it by my total charge, and that's going to give me total potential energy there. And so 1.2 joules per coulomb times 6120 coulombs is going to give me 7344 joules. Next, I'm going to go to a power calculation. And so how much power will the battery deliver if it does the 7344 joules of work consistently for the time duration of 3600 seconds? A change in work with a change in time is power. So what I'm going to do is simply put 7344 joules over 3600 seconds, and then that's going to give me 2.04 watts. Number of electrons calculation. So this is just kind of like a extra sort of a thing to do. It's definitely not necessary, but I did it anyways. How many electrons is 6120 coulombs of charge in the battery? So I'm going to take the total amount of charge, and I'm going to multiply that by N per amount of charge, and then I'm going to get back N. And so 6120 coulombs times 6.24 times 10 to the 18 electrons per coulomb is going to give me 3.82 times 10 to the 22 electrons. Now next, in order to verify what I've been talking about, at least in terms of power and energy, I am going to be using a test circuit for that. My test circuit just simply is this. It's a 1.2 DC voltage source going into a resistive load. And how do I come up with the value for that resistive load? I simply just took 1.2 volts and divided it by 1.7 amps to get 0.7059 ohms. The 1.7 amps is equivalent, of course, to 1700 milliamps. So this is my test circuit. So now I am going to do a power calculation based on the test circuit that I have. And so how much power will this battery deliver to the load if the voltage is at 1.2 volts and the current is at 1700 milliamps? So dW dQ times dQ dt equals dW dt, which equals power. And so what I have here is 1.2 volts times 1.7 amps equals 2.04 joules per second, which equals 2.04 watts. And so this is the same as before, so this checks out. Okay, so what does that resistor power plot look like? It looks like this. So you're going to be looking for, a positive power figure here because this is the resistive load, and when it receives power, that's going to be positive power. Okay, so we're right here at 2.05 and it's a little bit below that, so that checks out. That looks like exactly 2.04 watts, which is what we got here, 2.04 watts. So that checks out. Next, the energy calculation. So if the battery delivers 2.04 watts over the time span of 1 hour, how much total energy expenditure will this amount to? So the total amount of energy that it'll amount to is simply just integrating power between these two time points here and going from T0 to T1. And so what that gives us is 2.04 watts times 3600 seconds minus 0 seconds is going to equal 7344 joules. So this is the same as before, so this checks out. So the resistor energy plot. So I'm just going to take a look at that energy plot and see what it looks like when I plot it. And so since it's the energy of the resistor, that's going to be positive energy because it's receiving energy. And so this is what I have here, and that looks like our 7344 joules right about here at 3600 seconds. That looks like 7344 joules. It's just this is apparently 7K here, and so it's just a little bit above that, but not halfway through this division here, through this interval. So a little less than halfway through it. So that's looking like 7344 joules. So that is all that I have for this lecture, and hopefully it was helpful for you. Thank you for watching, and have a nice day.